Welcome to the National Science Foundation. I'm Josh Chamot. I'm here today with Stephen Ambrose, the founder and the head of technology for Asius Technologies. He and his colleagues have recently prepared two papers to present at the Audio Engineering Society meeting in London on May 14th. And the two papers describe both a new phenomenon of what we now understand may be going on inside the ear when you seal the ear canal with a speaker or other device, and also a technology that may help eliminate that effect. I want to start by just noting that this webcast is being recorded, but you can call in and join us at any time by pressing *1 on the touch-tone phone, and we'll put you in the queue for a question. And about an hour or two after the webcast, we'll have a version of this that you can use for any of the reporting needs. So Steve, let me go ahead and just start with you. What did you guys learn?
Well, we have a breakthrough discovery, we feel. Audiologists have been recently imploring us to turn down our personal listening devices. And we discovered why we should have to be told to do this. We don't have to be told not to touch a hot stove. That is something that we get pretty easily. So why would we have to be told to turn down these personal listening devices? And we discovered that there is an acoustic reflex in the ear which is triggered by sealing personal listening devices in the ear, and it automatically turns the volume down dramatically, which means that we are listening at dramatically higher volumes than we would in an open ear situation.
So if you're listening at these dramatically higher volumes, it's because what exactly is going on inside the ear? Why would we trigger the reflex? What's actually happening?
When a sound wave is moving just through air, it acts a lot differently than if a piston or speaker is sealed actually into a cylinder, which the ear canal is a cylinder. And sealing a speaker in the ear, that speaker now starts to act like a piston in a car engine. And you buy high compression car engines because they go faster.
Right.
But you don't want high compression waves in the ear canal. And we've actually filmed these volumes, and they are 50, often 60 decibels higher. 60 decibels would be 1,000 times higher in pressure, as well as the excursions impinged on our tympanic membrane. I think that we've noticed that people are used to seeing the tympanic membrane move in animations like the one behind us here.
Right.
And that is good for instruction, but you don't actually see the tympanic membrane move under conditions of normal hearing. That motion is on the order of 100 to 250 nanometers, which is billionths of a meter, and that's not visible except under extreme magnification. And we were able to put a video otoscope in the ear, and you can see this if you go online at www.asiustechnologies.com and click on the press release page. The motions of the tympanic membrane have been filmed with a speaker sealed in the ear, which shows visible motions quite obviously on the order of 1,000 times greater than they should be occurring. Now, those kinds of pressures in the ear, one would think, well, gosh, you'd only want to do that once. But there is a mechanism of the ear called the acoustic reflex. It's a factor of the stapedius reflex and the tensor tympani and some other factors. And it has the ability to attenuate the things that we're listening to 50 decibels. And that's quite a lot. So what happens is in sealing a speaker in the ear, when it's partially sealed or fully sealed, if I take my earbud that I use to speak on the phone and listen to music with, and sometimes I go in noisy environments and I will seal it that way, and there are these types of earbuds manufactured that are held by a headband in the ear to go in sideways. Or often this is the concha bowl of the ear, and often that's small on adults, children, and so you can't put this in your ear without partially sealing it. And the moment that it becomes partially or wholly sealed, these audio motions are then converted into oscillatory static pressures. And we publish these papers at the 130th Audio Engineering Society Convention, which is on May 13th in London. This discovery is published there. And in inventing the wireless in-the-ear monitors back in 1976, I mixed on stage for 40 years with lots of different professional bands. And we noticed that after 3 hours of performing that our ears would ache and we had audio fatigue, and this was markedly better than the loud volumes on stage that Pete Townsend and others have complained so much about real hearing damage from years of rock and roll. Well, the in-ear monitors that I invented protected us from those volumes. But I knew right away in the early days that even though I emulated the existing technology of sealing a speaker fully in the ear, as has been done for decades prior to that with hearing aids, that putting a full frequency speaker that had all of the highs and mid-range and the bass into an ear mold in the ear caused this pounding that many people hear if they put these in their ears. And you can't listen to them often as long as you would want to listen to, say, your home stereo speakers.
And you'd mentioned that's a phenomenon that people who have hearing aids have as well, and they've got some ways of jiggering around it where they'll put like holes in the devices.
Do vent the molds, and venting the molds gets rid of the pressures that are generated in the ear. Even if you just seal your ear, and then you'll hear your voice booming in your head. Now that's a magnification of sound, which also shows how this is being magnified, okay? If you hold your fingers in your ears and hear that booming, and then if you're very, very silent, you'll notice a rumble that comes from the fact that you can't really hold your fingers still enough to keep that rumble from sounding. So you're getting a rumble from your fingers, you're getting a rumble from your blood rushing through your body, your heart beating, body sounds. These are all there before you seal your ear, but once you seal them, they're 1,000 times louder. And those motions, being so tiny, are much, much smaller than the motions of a speaker, which are very visible if you take the grill off and look at it. You don't have to have a microscope, you can just see it moving from this far away. So we understood that this was an abnormal condition for the ear after using this on stage year in, year out for decades, and that it also had the music, it gave the music a muffled sound. When you shove things in the eardrum has a spring behind it, which is what you blow air into when you pop your ears.
You can actually refer on here.
There's the middle ear cavity here, and this forms an air spring, just an air cushion. But if you seal this part of the ear, this ends up being a smaller area and a stronger spring, and it holds the eardrum still. And that starts by holding the eardrum still so that it doesn't move the same way and it's not as sensitive to high frequencies. We noticed that no matter how we turned up the highs, we still couldn't get the kind of highs that you can hear in open ear situations.
Right.
Okay? But we solved this by an invention which I can show you here in one form.
Now this is, so when you say yourself, this is the technology that's now being reported in the paper.
This is it.
Okay.
Okay. Here we have a typical in-ear insertion earbud or monitor, and this is a very popular one. It just has a little ear tip that has a rubber flange.
But the design is identical to every other type of design that you could encounter, correct?
Most devices that don't use custom ear molds use that sort of an ear tip.
Yep.
Now this ear tip I have raised the flap on, and here we have a synthetic tympanic membrane. And you can see I'm trying to hold my fingers still, and I've sealed the end, and that's how much pressure is impinged on the tympanic membrane when you stick your finger in your ear or you seal it with an ear mold. And every time you move your jaw, those pressures can go up above 1,000 pascals or a kilopascal, which is, those pressures, when you pop your ears, you're sometimes making a pressure of about 3 to 4 kilopascals.
So what is this membrane? So the technology itself that you've developed is twofold. One is this membrane, one is the pump that inflates the other version. We'll get to that in a second. But just with the membrane itself, what is this modification? How did you arise upon this design, and what is this modification?
Well, we used biomimicry, and that we have a tympanic membrane that would normally be moving because of these pressures, and we filmed that. And so we took a medical grade polymer and we put an artificial tympanic membrane or eardrum into the ear tip, which absorbs these overexcursions and high pressures and allows the ear to be in a closed environment that feels to the eardrum like it's open, and it feels to the listener like it's open. And this doesn't trigger this acoustic or stapedius reflex that I mentioned earlier. And so your ear doesn't turn down its volume. And the volumes that are being recommended by both the audio industry as well as the medical communities these days, the lower volumes, now sound adequately louder and much more vibrant, a deeper, more resonant bass. The highs are quite distinct. And when you use the regular insertion monitors, they seal in the ear canal and act very much like, oh, you're probably old enough to have flown on the airplanes that, or the jets that had stethoscope tubes, and they had the speakers in the arms.
Right.
And before the kids popped the little membranes out, they had little eardrums on the ends. Now those moved just as much as the speaker, and they were a new sound source.
Right. There was no wire. It was just an air canal. Basically.
It was an air canal.
Right.
And when they didn't have the little membranes, then they sounded like a tube.
Right.
And when they did have the membranes, they got rid of a lot of that tube resonance because that membrane moved like the speaker, just as far, just as fast, so it was now a sound source. Now, when you seal one of these fully in the ear, then the membrane for that tube is the eardrum. And the eardrum starts moving half as much as the speaker, okay, sometimes 99% as much as the speaker, which is what the math shows and the formulas show in our papers. And when they do move that much, they are speakers at that point. And so the sound ends up, your eardrums are right behind your eyeballs. The sound ends up sounding like it's coming from your eardrums instead of from the speakers. So what does that do to the sound stage? It narrows it so it's only about that wide. Okay. And the minute you retrofit these earbuds with our Ambrose diaphonic ear lens retrofit, which is just an ear tip that can fit on, then all of a sudden the sound stage opens up. The instruments are where they ought to be. You don't have this throbbing, percussive bass banging on your eardrums.
Right.
You're not triggering the stapedius reflex. And your ear is much more sensitive. The stapedius or tensor tympani reflex or acoustic reflex, when it holds the tympanic membrane still, it's like taking a voltmeter and moving it from fine to coarse. And you can handle much greater voltages with coarse, but you don't see the detail. And so the eardrum, when it's held stiff, can handle much greater volumes, but it doesn't have the detail. So the minute those are absorbed by this artificial auxiliary tympanic membrane or eardrum, then it leaves your own ear able to listen at its normally high sensitive levels of open ears and is not overwhelmed by sound and is able to get that high definition.